Okay, so we have a problem here, a word problem, and this particular problem, it's a fairly common type of problem to see in math classes. So if you haven't seen one before, that'll be exciting. Okay, it says an open top box is to be constructed by cutting out squares from each corner of a 14 centimeter by 20 centimeter sheet of plastic, then folding up the sides. So what they're talking about is we're going to have a sheet of plastic or cardboard, you know, in this case they said plastic, and it's rectangular, and it's 14 centimeters by 20 centimeters. But then we're going to cut out a box, a square, you know, a square. They have to be the same in spite of my drawing. But those have to be, you know, an x by x squared. That would be then the area of that little square there. So the unit of measure here is just x, or the variable is x. It's x there and it's x there. It has to be a square, otherwise your box isn't going to line up right. So then think about scoring the plastic, you know, along here, so, and then along here, and along here, and along here. This becomes the base of the box, and then the sides fold up, and you have this rectangular box that you could put stuff in, okay? It doesn't have a lid, but, you know, that's why it says open top box. That's what they're talking about, okay? That we're doing this type of thing. We have a flat sheet, and we're going to cut out these corners, fold it up, and it's going to make a box. Okay. Find the size of squares that should be cut out to maximize the volume enclosed by the box. So how do you find the volume of a rectangular solid, we usually say, but how do we find the volume of this box? Well, let me write that a little bit differently. Let me first just give you volume. Volume is length times width times height for a rectangular, we usually call it a rectangular solid, but for the box, this volume is going to be length times width times height. Okay, so the length I have, so what is my length in this case? It's going to be the long one, so 20 minus, I have to take out this distance here and this distance here. So 2x, that's going to be the length. Okay, so I'm subtracting x here, and I'm subtracting x here. Oops. So I get 20, add 20 centimeters, and I'm taking out x centimeters on each end. Okay, so that's going to be the length. What's the width going to be? Well, the width is going to be 14 minus 2x. Because you've got the 14 inches here, but you're taking out x there and x there. Okay, so that's going to be the width. And then finally, what's the height going to be? How tall is your box? It's going to be x high. Because I'm not always great on drawing these boxes, but I didn't take a lot of art classes. Anyway, that's not too bad. So my length here is 20 minus 2x. My width is 14 minus 2x. But the height right here, the height of that box, is x. That's how much I cut out. I wanted to make a box so I could show you and stuff, but you could do that, you know, you get a piece of paper and try doing that, and that might help you understand the problem, or maybe you've seen these before. Okay, so now my volume in terms of x, so I'm writing this as a function, my volume in terms of x is going to be the length times the width times the height. I'm going to put the height first, x times 14 minus 2x times 20 minus 2x. Now if I wanted to, I could factor out a 2 from both that factor and from that factor. And I kind of want to. So I'm going to write this as 4 times 7 minus x times, oops, 4x. Forgot the x there. 4x, now it looks bad. This is important because this is our big equation here that we want. So the volume in terms of x, if I factor out common factors, I'm going to get 4x times 7 minus x times 10 minus x. So I factored out a 2 from there, and I factored out a 2 from there. 2 times 2 is 4, so I wanted to write it this way. I don't have to do that. I just thought it would be easier. Okay, now let's think about the graph of this. Well, it's volume, right? It's cubic. We know this is a cubic function. Or we should say the degree is 3. I don't want to call it cubic because I don't want you to get confused on the basic cubic function. Okay, so it has a degree 3. We could multiply it out and get a polynomial, but we know it has degree 3. We also know something about the x-intercepts. If I was to look at this graph, I have an x-intercept at 0. Okay, so my x-intercepts, I'm going to have one at 0, 0, right there. And that's coming from that, 4x equaling 0. I'm going to have one at 0, 7. I'm sorry, 7, 0. So I'll just draw 7. And I'm going to have one at 10, 0. 1 here. Now, because of the intercepts and the end behavior, if you think about the end behavior, it's going to be looking like this. It's going to have a positive leading coefficient. The leading coefficient, by the way, is 4x cubed, right? Okay, so you can think about that a little bit if you want to. I'm trying to put all the things that we've been learning in this chapter so far together for this problem, so that you can kind of see, like in a practical sense, if you wanted to make a box, you know how that would work. Okay, so we know it's going to come up here, it's going to go up, it's going to come down, and then it's going to go back up. We know that's the basic picture of our function. However, we need a positive output. We need a positive volume. So that's going to restrict to just right here. Okay? I'm going to have something between x. I've got to have x being between 0 and 7. Now, does that make some sense to us? Well, hopefully. First of all, if x was 0, then you didn't cut anything out of the box. You didn't cut a square out, so you couldn't make the box. And then it can't be bigger than 7 because that would make the width 0. Okay, you wouldn't have any width. So it's got to be somewhere between 0 and 7. Now here's where it gets a little tricky. The maximum is going to be right up here, you know. Where is that point occurring? We know it's somewhere between 0 and 7, but, you know, where does it occur? If you have a graphing calculator or technology, you can figure out where that is exactly. But I've kind of already talked about that it didn't require you to have a graphing calculator for this class. Now, you know, you might be saying, well, what about when I take calculus? Will I need it then? And you know, that'll be a different conversation with your calculus teacher. But what we can do is we can get kind of it narrowed down by hand without too much trouble. And then it'll give you an idea of what's going on. We've already put the pieces together from the stuff that we're learning right now to make it apply to this problem. But from here, the book is going to talk about, oh, get technology and, you know, figure this out. Okay, so, but I'm going to go show you what I would do without technology, basically. So I had a function, volume, in fact, it's right there, and I said 4x equals 7 minus x times 10 minus x. And that was my volume. So let's say I want to cut squares that are 2 inches. Let's see what kind of volume we get. So you'd have 4 times 2 times 5 times 8, right? Because you're subtracting 2 from 7 and then 2 from 10. And then you'd figure out what that was. 10 times 32 would be 320. So you're talking a volume of 320 cubic centimeters. Okay? And that would be, you know, how many cubic centimeters you would get if you cut out 2-inch squares. All right, let's see what happens at v of 3. Before I do that, let's graph that. So let's say this is 2. We'll count 2, 4, 6, something like that. And then at 2, we're having an output of 320. Okay, so let's say, let's not do 3, let's do 4, because that I have drawn. And you might say, well, how are you picking these numbers? Why don't you pick 3? I'm just randomly picking them. And I already did the calculations, so I thought it'd be easier just to make this video go quicker. You'd have 4 times 4 times 3 times 6. And then that multiplied out to be 288. So it looks like it's going down at 4. So, my graph is off, right? So let's say that's 3, and let's say that's 4. Okay, so now it's down here lower at 288. So, you know, there's a good chance that my x has to be somewhere between 2 and 4, right? And how do I know that? Because it's curving back down. I mean, it was going up. We know it started at 0 volume, and it went up to 320 right there when x was 2. But now it's down here at 4, and it's down at 288. So it's somewhere it had to make a turn, somewhere between 2 and 4. Okay, so now maybe I want to pick 3. All right. The volume at 3, you'd get what? 4 times 3 times 4 times 7. And I think that turns out to be 336. You'll have to check my math, but I think it turns out to be that. So at 3, it was a little bit higher. Okay, so here at 336. 336. So is it going up, you know, a little higher, or is it going to start coming down at 336? Okay, so then we kind of know, we don't know a whole lot. We know that it's going to be more than 2 and less than 4, and maybe around 3.3, you know, to get a maximum volume. Now from my picture, you might say, oh, well, it's going to be, you know, 3 centimeters. But we don't know exactly where that turning point is, okay? And that would be where you get the technology and you figure out exactly where it is. I think it's between 2 and 3, though, 2 and 3 centimeters. But it gives you an idea of how we use this and how it applies, and gives you a picture in a practical situation of what's going on, okay? So not an exact answer, but kind of gives you an idea. You can look in the book, and they'll show you a little bit more. They did more evaluations with decimal numbers. So.